the most powerful telescope ever built, pointed its golden mirrors at a frozen moon circling Jupiter. Scientists opened the data, and then the room went quiet. Not because nothing was there, because too much was there. Chemistry that shouldn't exist. Chemicals that radiation should have destroyed millions of years ago. Patterns so deliberate, so concentrated, so fresh that one geologist on the team reportedly said the data felt wrong, not broken. Alive. Tonight, we are going to Europa. A moon slightly smaller than our own, coated in cracked ice, bombarded daily by radiation that would kill an unshielded human in 20 minutes. A moon that has been sealed shut for 4.5 billion years. A moon that, according to everything James Webb just told us, is leaking. And what it is leaking from is an ocean. Not a small one. An ocean containing twice the liquid water of every ocean, lake, and underground reservoir on Earth combined. An ocean that has been sitting in complete darkness, under 20 miles of ice, completely undisturbed, running its own chemistry experiments since before complex life existed on our planet. We cannot see into it. No telescope can. No spacecraft has ever touched it. Everything we know comes from the breath of the moon itself, chemicals pushed up through cracks, salts left behind when ocean water freezes near the surface, carbon fingerprints rising from the deep. James Webb caught that breath. And what the telescope tasted in it is the reason thousands of scientists around the world are now leaning forward in their chairs. Here is what makes this genuinely unsettling. The chemicals Webb detected at the surface of Europa are not stable there. Jupiter's radiation tears apart molecules on a geological timescale. Whatever Webb saw had to be fresh, recently delivered, pushed up from below within the last few million years, which in cosmic terms is yesterday morning. That single fact changes everything. It means Europa is not a museum piece frozen in time. It is a living chemical engine, and we just caught it mid-cycle. Over the next several chapters, we are going to go deep into what Webb actually found, what it means, what it cannot explain, and what is heading to Europa right now to find out more. We will walk through the chemistry, the geology, the ocean, the seafloor, the radiation environment, and the two spacecraft now racing toward Jupiter to answer the question that Webb has made impossible to ignore. Are we alone in our own solar system? The data is coming in, the experiment is finishing, and the frozen moon 500 million miles away has been waiting for someone to ask the right question for 4.5 billion years. We begin. Picture a telescope the size of a tennis court floating 1 million miles from Earth, tilting its golden mirrors toward a small, icy world circling the largest planet in the solar system. That moment happened in 2022. The observation lasted only a few minutes. In astronomy, a few minutes is almost nothing. You usually need hours, sometimes days, to pull meaningful data from a distant object. Webb pulled more useful chemistry data on Europa in those few minutes than decades of previous missions combined. The reason comes down to what Webb was built to see. Infrared light, heat fingerprints, chemical fingerprints. The kind of light that carries the identity of molecules embedded in ice or drifting in a thin atmosphere. Every molecule vibrates at its own specific frequency in the infrared. Carbon dioxide vibrates one way. Sodium chloride leaves its own mark. Hydrogen peroxide has its own unmistakable signature. Webb reads all of these the way a trained ear picks out individual instruments in an orchestra. Before Webb, the Hubble Space Telescope had been our best tool for studying Europa. Hubble is brilliant, but Hubble sees mostly visible light. Europa's deepest chemical secrets hide in the infrared. Hubble was never built to read them clearly. Webb was built for exactly this. When the data came back from that first observation, the team expected mostly water ice, perhaps some sulfur compounds blasted onto the surface by Jupiter's radiation belts. What they got instead was a chemical map, a map showing specific substances pooled in specific locations, not spread evenly across the surface, concentrated, deliberate-looking, sitting precisely where the ice appeared most disturbed. The first chemical that stood out was carbon dioxide. CO2 has a powerful infrared signature. It vibrates at a frequency nothing else on Europa's surface fakes. The signal was clean, the signal was strong, and the signal was in completely the wrong place. Carbon dioxide on Europa's surface should not survive. Jupiter bombards that moon with radiation so intense it would kill an unshielded human within 20 minutes. That same radiation tears apart molecules. It destroys carbon dioxide on a geological timescale. Within a few million years, any CO2 left exposed should be broken back into its component atoms and scattered. So what Webb saw should not have been there, not unless something was constantly replacing it. The team ran the numbers. They looked at the concentration, the radiation environment, the rate of destruction. Their conclusion was unavoidable. The carbon dioxide on Europa's surface must have been delivered within the last few 100,000 years, possibly less. In cosmic time, that is the equivalent of finding warm footprints in fresh snow. The next question was where those footprints came from. 3 possibilities existed. The carbon could have arrived from space, carried by comets or meteorites. It could have been produced on the surface by radiation chemistry, or it could have come up from the ocean below. The team worked through each option methodically. Comets carry carbon, but comet impacts scatter material in radial patterns around a crater. Webb saw no such pattern. The carbon was tightly concentrated in one specific region, with no nearby impact site large enough to explain the distribution. Comet origin was effectively ruled out. Radiation chemistry can rearrange molecules but cannot manufacture carbon from nothing. You need a carbon source already present to start with. No evidence supported a large external delivery of carbon-bearing material. This pathway was also weakened. That left the third option. The carbon came from inside Europa, from the ocean. This was confirmed not just by the location of the carbon, but by its isotopic signature. Carbon comes in 2 main versions. Carbon-12 is common. Carbon-13 is heavier and rarer. Different processes leave different ratios of these 2 versions behind. Comets leave 1 ratio. Geological processes inside a moon leave another. Living things leave yet another. The ratio Webb measured at Europa matched internal planetary processing. It did not match a comet. It did not match interplanetary dust. It matched material that had been sitting inside Europa for a very long time and had recently been pushed to the surface. Samantha Trumbo at Cornell University, the lead author on the paper describing these findings, stated it plainly. Carbon is a biologically essential element. Finding observational evidence that the carbon on Europa's surface came from the ocean is not a trivial result. She was right to be careful with her words. It was not trivial at all. For decades, scientists were confident about Europa's water. They were fairly confident about its energy sources. The carbon, the third essential ingredient for biology as we know it, had been unconfirmed. Webb confirmed it. The pantry was stocked, the kitchen was real, and the recipe sitting on the counter was one that life on Earth would recognize. Not all of Europa looks the same from orbit. Most of the surface is smooth and bright, ancient ice crossed by long parallel ridges running for hundreds of miles. But scattered across the moon are regions where the surface has been completely destroyed and rebuilt. Regions where the ice looks like someone took a frozen lake, smashed it with a hammer, then let the pieces refreeze at wrong angles. Scientists call these regions chaos terrain. The name is not poetic. It is a precise geological classification describing what happens when an icy moon shell has been broken, rotated, partially melted, and refrozen, sometimes more than once. From orbit, chaos terrain looks like a jigsaw puzzle assembled by someone who lost the picture on the box. Europa has several of these regions, but one in particular drew Webb's most intense scrutiny, a region near the equator called Tara Regio. And Tara Regio is where the ocean is bleeding. The story of Tara Regio begins before Webb. The Hubble Space Telescope had already detected something unusual here years earlier. Hubble picked up the chemical fingerprint of sodium chloride, common table salt, concentrated in this specific region. Salt on an icy moon does not appear from nowhere. It tends to come from below, from a liquid source that has carried dissolved minerals up through the ice. When Webb pointed its instruments at Tara Regio, the salt story became far stranger. Not only was the sodium chloride still there, but now Webb detected carbon dioxide pulled on top of it in a sharp concentration, fading as you moved away from the chaos zone into the older, smoother ice surrounding it. Two chemicals, both from the deep ocean, sitting together in exactly the same broken patch of surface. The team led by Geronimo Villanueva at NASA's Goddard Space Flight Center published their findings in the journal Science. The carbon at Tara Regio came from below. It was deposited recently. The chaos terrain is where Europa's interior is communicating with its exterior. That word, communicating, is doing enormous work. Because if the ocean and the surface are exchanging material, then the ice shell is not a perfect sealed lid. It is a barrier with cracks, a barrier that breathes. Material is moving upward through those cracks, carrying the ocean's chemistry toward the surface where Webb can read it. And if material moves up, it can potentially move down. That downward direction is where things become genuinely exciting. Down is where the warm, dark water sits. Down is where, on Earth, life first appeared around hydrothermal vents on the ocean floor billions of years ago. To picture what Tara Regio actually represents, think of a freshly painted spot on an old rusted car. You would not assume the paint blew in from the wind. You would assume someone painted that spot recently. Tara Regio is the fresh paint, the ocean is the painter, and the paint contains the chemical signature of a world that is not sleeping. Now consider what Webb also found here that nobody expected. Hydrogen peroxide, the same reactive compound in the brown bottle in your medicine cabinet. On Europa, hydrogen peroxide forms when Jupiter's radiation splits water ice molecules apart and reassembles them. Scientists had predicted it would accumulate at the poles, where the ice is colder and the compound is more stable. Webb found the opposite. The highest concentrations of hydrogen peroxide were at the equator, specifically in Tara Regio. The warmer equatorial belt that should have had less peroxide somehow had more. This broke the working assumption that had been in place for decades. The team checked the instruments. They checked the data. The results stood. The puzzle was partially solved in 2024 when a graduate student named Bariset Mamo at the University of Texas at San Antonio ran laboratory experiments simulating Europa's surface conditions. He cooled ice to European temperatures, added trace amounts of carbon dioxide matching what Webb had detected, then blasted the mixture with radiation similar to Jupiter's output. The result was dramatic. Adding even small amounts of CO2 supercharged hydrogen peroxide production. Carbon dioxide acted as a catalyst, opening chemical pathways that do not exist in pure water ice. That solved the geographic puzzle. The hydrogen peroxide piles up at the equator because the carbon dioxide is at the equator and the two chemicals amplify each other's production. But solving one puzzle opened a much larger one. Hydrogen peroxide is a powerful oxidant. It is reactive and energy-rich. On Earth, oxidants are not optional for complex life. Our cells run on the energy released when oxidants meet fuel. Without something like hydrogen peroxide or oxygen gas, you cannot have animals. You cannot have most complex biology. Europa's ocean sits in permanent darkness, no photosynthesis, no sunlight driving chemistry. But if hydrogen peroxide generated at the surface can be transported down through the chaos terrain into the ocean below, then the deep water suddenly has access to a powerful energy source from above. Tara Regio is not just a chemical curiosity. It may be the delivery system for the energy that makes Europa's ocean livable. Stop for a moment and try to hold this picture in your mind. Beneath your feet, if you were standing on Europa, would be solid ice, not thin ice, not the kind you test carefully before stepping onto a frozen pond. 20 miles of ice pressing down in every direction. And below that ice, dropping down for another 60 miles, is liquid water. Not a lake, not a pocket, an ocean. One continuous body of liquid water wrapping the entire moon from pole to pole with no shoreline, no continent, no gap. The ocean covers every square foot of Europa's surface, sealed above by ice and resting below on a rocky seafloor we have never seen. Earth's oceans average about 2.5 miles deep. Europa's ocean averages around 40 times deeper. The total volume of liquid water on Europa is estimated at roughly 3 billion cubic miles. The total volume of liquid water on Earth, including every ocean, lake, glacier, and underground reservoir combined, is around 340 million cubic miles. Europa contains approximately twice as much liquid water as our entire planet. Let that land fully. Earth, the blue planet, the so-called water world of the solar system, is dramatically outclassed in liquid water by a frozen moon smaller than our own moon. The largest ocean in the solar system is not here. It is out there, hidden under ice, 500 million miles away. How do we know this without ever drilling through the surface? The primary evidence came from a spacecraft called Galileo, which orbited Jupiter from 1995 to 2003. Galileo flew past Europa multiple times and measured the moon's magnetic field on each pass. The readings were unusual. Europa was generating a magnetic response that could only be produced by a layer of electrically conductive material inside it. Salty liquid water conducts electricity. Frozen ice does not. The magnetic signal pointed to something liquid and salty sloshing around inside Europa with a high degree of confidence. Webb added the chemistry decades later. Salts on the surface, carbon dioxide leaking upward. The two data streams together, magnetic from Galileo and chemical from Webb, lock the answer in place. The ocean is real. The ocean is salty. The ocean is in contact with the surface. Now comes the part that should genuinely disturb you. We have no idea what is in that ocean. None. Every measurement we have is indirect. We are reading fingerprints on the outside of a frosted window. We have never seen what is in the room. On Earth, wherever liquid water exists, life exists. Every drop of seawater contains living cells. Every cave pool, every hot spring, every crack in Antarctic ice where liquid water persists, life is there. There is no known exception anywhere on our planet. Water and life have never been found separated from each other on Earth. Europa has water by the cubic mile. It has carbon now confirmed by Webb. It has salt matching what Earth's oceans contain. It has energy from Jupiter's tidal forces squeezing the moon constantly. It has a rocky seafloor that may host hydrothermal vents similar to those where life on Earth first appeared. Every box on the habitability checklist is being ticked. Not theoretically, not in models, in actual data returned by the most powerful space telescope ever built. The ocean also has a feature that makes it particularly interesting compared to other proposed habitats in the solar system. It is in direct contact with rock. Europa's seafloor is stone, heated by tidal forces, potentially volcanic in places. When liquid water touches hot rock, minerals dissolve. Chemicals react. Energy is released. On Earth, this exact process, hot water meeting rock at hydrothermal vents, is where many origin of life researchers believe biology first emerged. Europa is not like Ganymede, Jupiter's largest moon, which also has a subsurface ocean, but one sandwiched between layers of ice, isolated from any rocky seafloor. Europa's water sits directly on stone. The chemistry of rock and ocean has been running there for 4.5 billion years. The ocean also gets energy from above. Webb confirmed that hydrogen peroxide is forming at the surface and that the chaos terrain is exchanging surface and subsurface material. If oxidants from the top can reach the ocean, the water below has both vent chemistry from the seafloor and oxidant energy from the surface. That is, two independent energy sources feeding the same body of water. On Earth, complex ecosystems exist around deep-sea vents, powered entirely by chemistry with no sunlight required. Those ecosystems support bacteria, tube worms, shrimp, and entire food webs. Europa's ocean could support at least the microbial base of such a system. We are not saying life is there. We are saying there is nothing on the list that would forbid it. And the list is long, and Europa is checking every item. The experiment has been running for nearly 5 billion years. Webb just told us the laboratory is still active. The next question is what the experiment has produced. Most people picture ice as something that simply sits there. Cold, solid, unchanging. A frozen pond does not rearrange itself overnight. A glacier moves, but slowly, over centuries. You would expect a moon coated in 20 miles of ice to be the most static, boring geological object imaginable. A frozen vault sealed shut since the early solar system. Europa's ice does not work that way. What James Webb found on the surface, combined with data from the Juno spacecraft's close flybys in 2022 and 2024, has forced scientists to completely rethink what Europa's ice shell actually is. It is not a clean, smooth barrier. It is not a uniform block of frozen water pressing down on the ocean below. It is a fractured, porous, chemically complicated material that is constantly being rebuilt from the inside out. It is, in the most precise scientific language available, a shell that breathes. The first clue came from something Webb detected that should have been impossible. Crystalline ice and amorphous ice sitting side by side in the same regions of the surface. Here is why that matters. Amorphous ice forms when water freezes too quickly or under too much radiation for the molecules to organize themselves. The result is a chaotic jumble. Water molecules frozen in disorder like a crowd caught mid-stampede. This is the natural product of Jupiter's constant radiation bombardment. On any icy moon bathed in that kind of particle radiation, you expect amorphous ice to dominate. Given enough time, radiation should grind every crystal of ordered ice into disordered mush. Crystalline ice is the opposite. It forms when water freezes slowly and the molecules have time to arrange themselves into neat, repeating patterns. This is the ice in your freezer. This is what you find on Earth, where conditions are stable and radiation is gentle. On Europa, in the full blast of Jupiter's radiation belts, crystalline ice should not last more than a few thousand to tens of thousands of years before being scrambled into amorphous disorder. Webb saw both in significant quantities in the same locations. The team led by Ujjwal Raut at the Southwest Research Institute reported this finding and had to grapple with what it meant. The crystalline ice could not have been sitting there for long. Radiation would have destroyed it, so it had to be continuously refreshed. Something was constantly delivering fresh, ordered ice to the surface faster than radiation could disorder it. That refreshment can happen in only a few ways. The surface could be periodically warmed by tidal flexing concentrated in chaos regions, allowing ice to recrystallize before radiation fully disorganizes it. Or fresh water could be delivered from below, freezing into crystalline ice as it reaches the slightly warmer environment near the surface. Most likely both processes are happening simultaneously in different locations and at different rates. Both explanations feed the same conclusion. Europa's surface is not a static ancient record. It is being continuously refreshed by activity from below. The ice we see today is geologically young, possibly only millions of years old in places, on a moon that is 4.5 billion years old. The Juno spacecraft added another layer to this picture. Its microwave radiometer, an instrument that reads the natural microwave emissions of objects and can penetrate ice that visible and infrared light cannot, scanned Europa's upper shell during its flybys. The team led by Stephen Levin at NASA's Jet Propulsion Laboratory published results in late 2025 in the journal Nature Astronomy. The ice shell is approximately 18 miles thick on average, with significant uncertainty of plus or minus 6 miles. But more importantly, the upper ice is riddled with tiny scattering features: pores, bubbles, stress fractures, voids. None of them large by themselves, but together painting a picture of ice that is structurally complicated throughout its upper layers. To understand the difference, picture two blocks of frozen water. One is clear and smooth, like the ice in a high-end cocktail glass. The other is cloudy and full of tiny air bubbles and stress lines, like the ice that forms in a household freezer over weeks. Juno's readings suggest Europa's upper ice looks far more like the second block. The shell is not a clean window. It is a textured, fractured, porous material with internal structure at every scale. This matters for the chemistry story directly. A porous, fractured upper ice gives materials from below more pathways to approach the surface. Carbon dioxide, salt, and hydrogen peroxide all have an easier time arriving at the top if the ice is not a perfectly solid wall. Webb's chemical detections make more sense when you understand that the barrier they crossed was already compromised. The Juno team noted that the tiny pores and cracks in the upper layers are probably too small individually to act as highways for large-scale ocean-to-surface transport. Microbes from the deep ocean probably cannot simply swim up through them, but chemistry behaves differently from biology. Gases and dissolved compounds migrate through tiny pathways over geological timescales, even when nothing larger can follow. The shell that blocks organisms may be perfectly permeable to molecules. And in the chaos terrains, the disruptions are far larger than tiny pores. Whole blocks of ice the size of cities have been broken, rotated, and refrozen. Those events almost certainly reach down toward the ocean. When they do, water from below can squeeze upward, freeze near the surface, and deposit the chemistry Webb detected. The shell is not a wall. It is a membrane. Imperfect, dynamic, constantly being rebuilt, leaking chemistry in both directions on a geological clock that has not stopped running. Whatever is below has been slowly, steadily exhaling through that membrane for billions of years. Webb just gave us the instrument sensitive enough to smell the breath. 60 miles below Europa's surface, past the ice, past the dark, cold water of the ocean above, there is a rocky seafloor. We have never seen it. No spacecraft has measured it directly. No instrument has ever come close to it. Everything we know about it is inferred from the moon's total mass, its density, its magnetic behavior, and the chemical fingerprints it leaves in the ocean water above it. But what we can infer is enough to make Europa's seafloor the most scientifically compelling piece of real estate in the outer solar system. Europa's interior beneath the ocean is rocky. That rock is being heated continuously by the same tidal forces from Jupiter that keep the ocean liquid. The moon flexes every few days as it moves through its slightly oval orbit, closer to Jupiter and then farther away, stretching and relaxing under the pull of the giant planet's gravity. That constant flexing generates heat the same way repeatedly bending a metal wire generates heat. The energy goes into the rock. The rock stays warm. And warm rock in contact with salty water produces something very specific: hydrothermal vents. On Earth, hydrothermal vents sit on the deep ocean floor where volcanic and geothermal activity heats the rock below. Cold seawater seeps down into cracks in the seafloor, gets heated to extreme temperatures, dissolves minerals from the surrounding stone, and then erupts back into the ocean as scalding, mineral-rich plumes. The water that comes out is chemically transformed. It carries sulfur, iron, manganese, and dozens of other compounds stripped from the rock below. Around these vents, entirely cut off from sunlight, Life thrives on Earth. Bacteria form thick mats on the rocks near vent openings. Tube worms grow to extraordinary lengths, feeding on those bacteria. Strange shrimp, crabs, fish, and other creatures form complete ecosystems powered entirely by chemistry, not sunlight. When marine biologists first discovered these systems in 1977, it rewrote the fundamental rules of where and how life can exist. Before that discovery, every known ecosystem on Earth ultimately depended on sunlight. Plants captured solar energy, animals ate plants. The chain always traced back to the sun. The vent ecosystems destroyed that assumption completely. They proved life could be powered by the energy released when hot mineral-rich water met cold seawater. No sun required. Many origin of life researchers now believe that Earth's first living cells may have emerged at or near hydrothermal vents. The deep ocean floor of the early Earth, 4 billion years ago, was a chemistry laboratory running continuous experiments at thousands of vent sites simultaneously. The water was hot, the minerals were rich, the chemical reactions were constant. At some point, in some location, one of those reactions produced a molecule that could copy itself. From that single event, every living cell on Earth descended. Now, look at Europa. Rocky seafloor, confirmed by density measurements. Tidal heating from Jupiter, generating warmth continuously. Salty ocean water in direct contact with that warm rock for 4.5 billion years. The conditions for hydrothermal venting are not just possible on Europa. They are expected. The chemical evidence Webb found at the surface supports this. The unusual salt composition at Tara Regio, dominated by sodium chloride, rather than the magnesium-rich salts that models initially predicted, suggests the ocean's chemistry has been shaped by specific processes at the seafloor. Hydrothermal activity would do exactly that. Vents produce different mineral outputs depending on the rock type and temperature involved. The salt fingerprint Webb detected at the surface is the kind of signature you would expect from an ocean that has been chemically processed by rock-water reactions at the bottom for billions of years. The carbon dioxide Webb found also fits. Carbon dioxide is a natural product of certain seafloor chemical reactions, particularly the kind that happen when seawater interacts with iron and magnesium-rich rocks in a process called serpentinization. This process does not require biological input. It is pure geology, but it produces exactly the kind of carbon-rich, chemically active water that biology would find useful if biology were present to take advantage of it. Picture the seafloor in complete darkness. Pressure so extreme it would crush conventional submarines. Temperature swinging from near freezing in the open water to several hundred degrees at the mouths of active vents. Mineral chimneys rising tens of feet from the seafloor, releasing black plumes of superheated mineral-rich water into the cold ocean above. And around those chimneys, if Europa resembles Earth in this respect, microbial mats. Films of single-celled organisms drawing energy from the chemistry the vents provide, feeding on sulfur and hydrogen and carbon, living their entire existence in complete darkness with no awareness of the ice above or the universe beyond. We cannot confirm this picture yet. We can only say that the chemistry leaking to the surface is consistent with an active seafloor below, strongly consistent, consistently enough that both NASA and the European Space Agency have committed billions of dollars and decades of effort to finding out whether that picture is accurate. There is one more dimension to the seafloor story that Webb's findings illuminate. The combination of vents from below and oxidants from above gives Europa's ocean something rare among potential habitats in the solar system. Two independent energy sources, chemical fuel from the seafloor delivered by rock-water reactions at the vents, oxidants from the surface generated by Jupiter's radiation and transported down through the chaos terrain over geological time. On Earth, complex ecosystems exist when you have both fuel and oxidants available. Our own biology runs on this combination. Fuel in the form of food meets oxidants in the form of oxygen, and energy is released. Europa may have both ingredients in its ocean simultaneously, one rising from the rock below and one descending from the ice above. If that is the case, Europa's ocean is not just a possible habitat, it is a powered one. An ocean with chemistry flowing in from two directions, meeting in the water column, running reactions, releasing energy, the same basic setup that on Earth eventually produced us. In October of 2024, a spacecraft the size of a basketball court lifted off from Kennedy Space Center in Florida and began the long journey outward toward Jupiter. Its solar panels, the largest ever flown on a planetary science mission, stretched nearly 100 feet from tip to tip. They had to be that large because at Jupiter's distance from the Sun, sunlight is 25 times weaker than it is on Earth, and this spacecraft needs every photon it can collect. Its name is Europa Clipper. It is the most ambitious mission ever built to study a single moon, and it carries the collective scientific ambition of thousands of researchers who have spent careers trying to understand what is under Europa's ice. Clipper will arrive at Jupiter in 2030. From there, it will spend several years performing approximately 50 close flybys of Europa, each one bringing the spacecraft within a few dozen miles of the surface. At those distances, instruments can read chemistry, map geology, and probe the magnetic field in detail that no telescope, including Webb, can match from a distance. Webb gave us the overview. Clipper will give us the close-up. The spacecraft carries 9 primary scientific instruments, each designed to answer a specific piece of the Europa question. The mass spectrometer, called MASSPEX, will analyze the thin atmosphere that surrounds Europa. This atmosphere is not substantial. It is essentially a whisper of gas created when Jupiter's radiation kicks molecules off the surface. But that whisper carries chemical information directly from the surface and possibly from below. MASSPEX is sensitive enough to detect complex organic molecules if they are present and to measure their isotopic ratios. If biological processing has left a chemical fingerprint in Europa's atmosphere, MASSPEX has a genuine chance of detecting it. The ice-penetrating radar called REASON will do something no instrument has ever done at Europa. It will look through the ice. Radar waves penetrate frozen water in ways that visible and infrared light cannot. REASON will map the internal structure of the ice shell, identifying layers, measuring temperatures at different depths, and searching for pockets of liquid water trapped within the shell itself. If internal lakes exist inside Europa's ice, REASON should find them. If the shell shows signs of active convection, with warm, soft ice rising and cold, brittle ice sinking, the radar will reveal the layered structure that convection produces. The magnetometer will refine what Galileo's measurements suggested decades ago. By measuring Europa's magnetic response in far greater detail across dozens of flybys, it will determine the ocean's depth, salinity, and how the ocean's properties vary across different regions of the Moon. A saltier ocean produces a stronger magnetic response. A deeper ocean produces a different signature than a shallow one. The magnetometer will effectively take the ocean's vital signs from the outside. The thermal imager will hunt for warm spots. Locations on the surface where heat from below is closer than average to the top. Warm spots indicate thinner ice or active geological processes pushing heat upward. They are also the most likely locations where ocean chemistry is currently arriving at the surface. Webb identified Tara Regio as a chemically active region. Clipper's thermal imager will tell us whether heat is concentrated there too, and whether there are other warm spots Webb's resolution could not resolve. The surface imager will photograph Europa at resolutions dramatically higher than anything we have today. The chaos terrains that Webb identified as chemically important will be mapped in detail. Individual ridges, lenticuli, and chaos blocks will be resolved clearly. The geological history written into the surface will become far more readable. Together, these instruments form the most comprehensive investigation of a potentially habitable world ever mounted by a single spacecraft. But Clipper has one significant limitation that is worth being honest about. It is not a lander. It will never touch Europa's surface. It will never scoop ice or drill into the shell. All of its science will be done at high speed during flybys, each one lasting only a few hours before the spacecraft sweeps past and begins preparing for the next pass. This matters because the most direct way to confirm life would be to physically sample the chaos terrain material, the ocean chemistry deposited on the surface over geological time. Clipper cannot do that. What it can do is identify the best locations for a future lander to touch down, characterize the radiation environment a lander would have to survive, and map the surface geology in enough detail to determine where ocean material is closest to the top. There is also the plume question. Webb did not detect active plumes during its observation. But plumes might be variable, erupting only at certain orbital positions when Jupiter's tidal forces are strongest. Clipper will fly through Europa's space environment dozens of times at different points in Europa's orbit. If plumes exist and happen to be active during one of those flybys, mass specs will taste them directly. That would be the closest thing to a direct ocean sample any mission has yet achieved. Webb gave Clipper a crucial head start. Clipper now arrives at Europa knowing where to look. Tara Regio and the other chaos terrains are already flagged as priority targets. The chemistry Webb detected will be the baseline against which Clipper's measurements are compared. If MassSpecs finds the same carbon compounds Webb detected, but in far greater chemical detail, the picture will sharpen dramatically. The mission's primary goal is not to detect life. It is to determine definitively whether Europa's ocean is habitable. That answer, when it comes, will decide whether a follow-up lander mission gets built, whether humanity commits to the next step, whether we eventually get a submarine through that ice. Clipper is not the end of the Europa story. It is the beginning of the serious chapter, and it is already on its way. Imagine a Tuesday morning, sometime around 2035, a press conference somewhere in Washington or Houston, or perhaps simultaneously, broadcast from a dozen cities at once. Scientists standing at a podium, a slide on the screen behind them, a graph, a chemical readout. Careful language in the paper published that morning, wrapped in the kind of scientific caution that takes years to earn. But the headline writers have no trouble with it. Life detected beyond Earth. Or imagine the opposite, years of data. Clipper finishing its mission, a lander touching down on chaos terrain and scooping ice that came from the ocean below. Every instrument reading, every signature analyzed, and the final verdict delivered just as carefully, just as honestly. Nothing. Europa is sterile. Both of those mornings are coming. One of them is real. And whichever one arrives, it will be one of the most important sentences a human being has ever spoken out loud. If life is there, the implications do not stop at Europa. Life arising independently in two places inside the same solar system means the universe is not empty. It means the conditions for biology translate into actual biology wherever they persist long enough. The Milky Way has hundreds of billions of stars. Many of them have icy moons with hidden oceans. If Europa's ocean produced life from the same ingredients Earth used, those other oceans almost certainly did too. The universe stops being a vast, silent place with one lucky exception. It becomes a place saturated with life at the microbial level, and somewhere in its enormous reach, almost certainly rich with something more complex. We would no longer be alone, not even in our own solar system, not even in our own backyard. And if Europa is dead, that answer is its own kind of horror. Same water as Earth, same carbon, same energy, same 4.5 billion years, and nothing to show for it. That outcome forces a question science cannot currently answer. What is missing from the recipe? What specific ingredient does life require beyond everything Europa already has? Finding that missing piece would become the defining scientific pursuit of the century. And the answer, whatever it turns out to be, would tell us something devastating about how rare and fragile and irreplaceable life on Earth truly is. There is a third possibility, the one that is honestly most likely in the near term. Gray. Ambiguous. Clipper returns data showing organic chemistry that looks biological but cannot be confirmed. Isotope ratios consistent with life but not proof of it. Complexity in the surface chemistry that exceeds geology alone but falls short of a verified detection. That gray zone is where science lives before the resolution comes. It can last years. It can last decades. It demands patience that does not come naturally to a species that wants answers. Webb has already moved us into the early edges of that gray zone. Strange chemistry rising from a hidden ocean. Carbon that should not be there. Salt that matches what Earth's oceans contain. Hydrogen peroxide pooling in exactly the wrong place for every model that came before. A surface rewriting itself faster than radiation can destroy it. A shell that breathes. A seafloor we cannot see but whose fingerprints are all over the ice above it. None of that proves life. All of it points toward a world where life is not forbidden. And that shift, from forbidden to not forbidden, from unlikely to entirely possible, is what those few minutes of Webb observation actually accomplished. The moon has been sitting out there for 4.5 billion years, sealed under ice, dark, running whatever experiment it has been running since before the first complex animals walked on Earth. It did not know anyone was looking. It did not know anyone existed to look. It has just been doing what it does, breathing chemistry through its cracked shell, letting its ocean press upward through the chaos terrain, leaving salt and carbon and the fingerprints of something vast and hidden on its frozen face. Now we are looking. Webb is watching. Clipper is on its way. And in the next decade, the quiet frozen world, 500 million miles from where you are sitting right now, is finally going to give us something close to an answer. Either we are not alone in our own solar system, or we are alone in a universe far stranger and far emptier than we ever wanted to believe. Either way, nothing stays the same after that morning. The ice has been keeping its secret for nearly 5 billion years. It will not keep it much longer.